guys, welcome to your final video of day 14. We are looking at area and we are on page 207 of the course packet. At the top of this page you guys are going to see some area formulas that you've probably seen before. Some of them may be more than others. The area of a parallelogram is the same area formula as a rectangle or a square, just base times height. Triangle is 1/2 times base times height. Trapezoid has two bases, because remember you have those two bases that are parallel to each other, the smaller base and the bigger base. And then you have a kite, which has the area formula related to your diagonals, which are those two lines I drew, and that are typically what you think of as like the sticks that hold a kite together. And these are all formulas that if you are curious, oh, and of course circle, pi r squared. And these are formulas that if you're curious, looking into a proof for the formulas is a really interesting thing to dive a little bit deeper. So that's kind of like an extension. If you are interested, you can look up videos involving proofs of those formulas because they are pretty interesting for how you get to them. There's also a formula that the Competition Math for Middle School book does cite called Heron's formula, and I put it here. And it's for the area of a triangle given side lengths A, B, and C, and the semi-perimeter, which is half the perimeter. So, add it all up, divide by 2. And this one's an interesting formula because it does not rely upon having, a base and a height. It only uses the side lengths. So this would also be another interesting proof to look into. Many interesting area problems involve addition and subtraction of overlapping regions, as well as applying the Pythagorean theorem. So overlapping regions will be really useful for you guys as a back pocket tool, especially if you are doing a competition problem involving a shaded area region, right? Being able to subtract certain areas from each other. This example is something called a lune, really weird term. And we are looking for the shaded area below. So we have ABC, AXB, and BYC are all semicircles. They give us some dimensions. So AB is 8, so I'll put it here. BC is 12. And we want to find the combined areas of the shaded regions. Now, notice, there's a lot of things going on here. We've got triangle, we've got semicircles. So typically the best way is to figure out a plan of how to get that little chunk that we want. Now, if you look, what we could do is we could try and just get the semicircles, right? This guy and this guy, and subtract the other stuff to get it out. But there's not an area formula for just that little bit. So what we need to do is, I'm going to do like the small plus the medium semicircle, because notice there also is this larger base semicircle there. And we also want to add that triangle as well, that right triangle. And that would give us everything. And then if I just want the shaded region, I would subtract the large semicircle. So that's the way to strategize, and that's kind of what it was getting at up above. So now we actually have to find these areas and then combine them in the fashion that we've outlined above. So your small semicircle area, we're going to do the area of a circle, which is a full circle is equal to pi r squared. So a semicircle is going to be pi r squared divided by 2. So your smaller one, radius is 4. So it's going to be pi times 4 squared, which is 16, but divided by 2, that's going to give us 8 pi. And then your medium circle is going to be the same thing. Your radius of that is going to be 6, so it's going to be pi times radius of 6 squared, which is 36 pi, divided by 2, and that's going to be 18 pi. And then your triangle, notice if I want the area of a triangle, your base and your height have to make a right angle. And so if you kind of turn it, you could view it more as having the 8 and 12 making a right angle there. And that's your base and your height. So your area is 8 times 12 divided by 2. So 8 divided by 2 is 4, times 12 is 48. And then we need the area of our large semicircle. And now the trick with this one is they don't give us the diameter, which helps us get the radius. So we need to use Pythagorean theorem to find the third side of our right triangle, doing 8 squared plus 12 squared equals c squared. That looks like it's 100, 200, and 8. Okay, so on my calculator. And it looks like it does not come out cleanly, which kind of stinks there. So what I might do is I might leave it as the square root of 208 for now. We could also see if 208 has any perfect squares, like if 16 fits into it. Oh yeah, so I could make it square root of 16, square root of 13. That would give me 4 square root 13, and that's kind of nicer to look at. So let's have that be our diameter. So that means my radius would be half of that, so 2 square root 13. So for the area of the large, we're going to have, sorry about that, pi times radius, and radius is 2 root 13 squared divided by 2. That's going to be equal to pi times 2 squared times 13, because that's under the square root, all divided by 2. So the 2 and the 4 is going to make it 2, so it's going to become 26 pi. So it looks like we're going to have 8 pi plus 18 pi plus 48 plus 26 pi. Oops, sorry. Minus, that's coming from up here, that minus sign, because we want to combine everything and then take out the middle part that we don't want. 8 plus 18, and then we're going to do the minus 26. Oops, and don't know where the 2 went there. Which actually makes 0, which is really interesting. So these all perfectly cancel out, and it becomes 48 centimeters squared is our final answer. And notice things like your square root, leaving it in a square root rather than rounding it decimal. If you rounded it as a decimal when you were finding the radius of the large semicircle, that would have changed your answer and made you off by a little bit. So you probably wouldn't have gotten 0. When you subtracted, you would have gotten a small decimal. It's a really interesting problem. And then the last couple things I want to show you guys, there's just 2 more over here. So a big part of area problems, especially in geometry, is called working backwards. And working backwards problems often give you the area and ask you to backtrack and find a certain measurement. So finding the area of a figure can often be useful when you're looking for additional information. We want to find the length of the altitude to the hypotenuse of the 5, 12, 13 right triangle. And sometimes we call triangles like that if it is a Pythagorean triple. Pythagorean triple are 3 sides that make a right triangle. So oftentimes we talk about the very common 3, 4, 5 right triangle, because 3 squared plus 4 squared is 5 squared. That's the smallest right triangle that we've got. That's got nice whole numbers. So find the length of the altitude. So we're looking for this guy here. So the hard thing is how to do that. And what we like to do with area working backwards is to find the area. So the area of this triangle is base times height divided by 2. These 2 make a right angle, so I could do 12 times 5 divided by 2. That's going to make 6, so it's going to be 30 units squared. And now I know that another way to find area, it's kind of like 2 different ways to find area, is 13 times the height divided by 2, which we don't know. Now that area is also going to be equal to 30 because the area is the same. We're just using a different base and height in order to find it. So in addition to kind of working backwards, this is also kind of like area in 2 different ways. using two different area pairs, a base and a height, to find missing information. So it looks like this is not going to come out super clean. Yeah, so it looks like it's about 4.62. Which is okay. It's not super clean, but that's okay. Next one. What is the area of the circle inscribed within a triangle of area 30? So we know that the triangle's area is 30, and we know that the perimeter is 30. And that's not a ton to go on. We're looking for the area of the circle, so that means we have to find r, right? We need to find the radius. And we don't really have a ton to go off of. So I'm trying to think of my area formulas and how that might help me. I know that the triangle's area is 30, and if I could do base times height divided by 2, right, equals the 30, that might help me. But the problem is that I don't really have any measurements, and I don't really have a good way to find a height. So one thing that I'm noticing is that this triangle is kind of broken up into 3 little ones. So I could do the area of this triangle. The area of this triangle is my base, AC, times my height divided by 2. So kind of base times height divided by 2. Okay. I could also add to that the area of this one here, plus base is AB times height. Now, notice in this case, my height in the first one and my height in this one is actually r, so I really should switch that to radius divided by 2. Same kind of thing for this one. I could do base times height, which goes from the center straight down, so that's your radius divided by 2. And that adds up to be the area of the triangle, which they told us was equal to 30. Now what's kind of nice about this is there's some commonalities, so let's take out a greatest common factor. A greatest common factor would be radius divided by 2, and then that would be times AC plus AB plus BC is equal to 30. Now notice AC plus AB plus BC, that's the perimeter of the triangle. And the perimeter of the triangle they already told us was 30. So from there, we've got 30 times radius over 2 is equal to 30. And that's saying if I simplify here, 15 times radius is 30, which means your radius, you could conclude, is 2. So from here, if I want to know the area, it's going to be pi times the radius of 2 squared. So your area is 4 pi centimeters squared. And that's our last problem. Congratulations, guys. That is the last video lesson for the Competition Math Summer 2020 course. I will see you guys tomorrow, and we'll do some area practice. We'll do some planning for the expo to get ready. So have a great night.